Hello, I'm Philipp from Münster University and I present the results of our study in which we investigated which aspects of program comprehension may also be involved in algorithm comprehension and what aspects may be different. For us, an algorithm consists of three components. The first component is a description of a well-defined problem. Second component is a description of a process that solves that problem. It may be presented as pseudocode or precise prose. Third component is a chain of reasoning, arguing about a property of the process, such as its correctness or its efficiency. The proven property is not obvious for the intended reader, and therefore the proof is necessary. Students have to understand algorithms, because they are an essential part of various areas in computer science. Knowing more about algorithm comprehension can support students' learning in such situations. Unfortunately, we don't know much about algorithm comprehension, but we do know a lot about program comprehension. For example, we know that nuances such as the length of code or the existence or lack of additional information may impact program comprehension significantly, since, by the above definition, there are very clear differences between an algorithm and a program. We conducted a study to investigate whether, and if so, to what extent, these differences impact comprehension. For this, we conducted a larger grounded theory study, part of which we discuss in our paper. The first phase aimed at getting a broader picture of algorithm comprehension. For this, we conducted semi-structured interviews with 3 PhD students who had experience in research and teaching. Findings from this study were used to design and analyze Think Aloud interviews with 6 computer science students with different levels of experience. During those interviews, they were asked to read the KMP algorithm and to perform a transfer task. This textbook algorithm solves a pattern matching problem in a non-obvious way and thus requires a proof of correctness. To broaden the scope of the study, we conducted additional Think Aloud interviews with students from an even larger range of backgrounds. In these interviews, the algorithm addressed an everyday situation. Imagine you only have 1, 2, and 5 cent coins and someone asks you to return change. And now you have to return the minimal number of coins. The algorithm solved the problem greedily by returning as many coins of the biggest denomination first. After that, it continues with the second largest denomination and so on until the value of the returned coins equaled the change that had to be returned. This solution obviously returned the right change, but the optimality, which depends on the property that the denomination of coins decreases at least geometrically, required a proof. All interviews were analyzed using grounded theory. Hence, analysis and sampling of data was interleaved. See the paper for more details. Let me quickly relate some findings to program comprehension. From program comprehension research, we know that programs are understood on both a very high level and a very detailed level of abstraction. It is therefore no surprise that our expert interviewers described that comprehension of the process requires understanding it both on a level detailed enough to implement it and on a level abstract enough to briefly summarize it. We would expect from program comprehension research that short code, such as the code describing the process of the KMP algorithm, would be read without even looking at additional material. However, we observed that all participants, even if they were confident in understanding the process from the code alone, required the additional material provided by the textbook in order to comprehend the process. We conjecture that the complexity of the KMP algorithm consists in understanding why it solves the problem at all, which, by definition, requires a proof. Overall, we observed some effects of the proof on top-down and bottom-up comprehension strategies to resemble effects known from program comprehension. For instance, PhD students described the prose as a source for high-level goals and refinements, which enrich top-down strategies. We also observed that figures illustrating the algorithm triggered plan schemata of how the process may work or how a naive algorithm could solve the problem. Especially when sections of the code were understood in isolation, the additional material helped connecting them, hence affecting bottom-up strategies. In various areas, including program comprehension, transfer tasks are utilized to assess the result of the comprehension process. Hence, we ask each participant to transfer the algorithm they had read before to a related problem. For the coin-changing algorithm, the task was to solve the same problem for a different set of denominations: 4, 3, and 1 cent coins. The set was chosen such as to violate the conditions necessary for the algorithm's optimality. 4 is not at least twice as large as 3. The original algorithm thus would greedily incorrectly represent 6 cents by 1 4-cent and 2 1-cent coins, whereas the optimal solution would use only 2 3-cent coins. During the Think Aloud interviews, we observed that one participant comprehended the procedure of the coin-changing algorithm on high and low levels of abstractions. He then adapted the procedure by returning 4 cents instead of 5 and 3 cents instead of 2 cents. However, this solution does not return the optimal coin set because the property considered in the proof of correctness was violated in that new problem. Hence, a description of a well-comprehended algorithm needs to take such properties into account. In conclusion, the comprehension of the process description resembles comprehension of programs. However, strategies known from program comprehension are affected by the complexity of some algorithms and the additional material provided. Eventually, we illustrated that algorithm comprehension needs to include the comprehension of certain properties and hence goes beyond program comprehension. Thank you. Comprehension.
Okay, great study. We have Philip with us. So the first question is that from Alexander. Can you argue that understanding a procedure is more complex than understanding a proof or other way around? Or are these completely different type of cognitive activities that one cannot even compare?
That's a very interesting question. I think both are different parts of algorithm comprehension. So you need to understand the procedure and you need to understand the proof. I don't want to talk too much about the complexity because I don't have a proper metric to measure complexity of proofs and of programs, even though I know that there are complexities or that there are metrics for complexity already. For example, one was published by not a co-author of this, but of another study by Rodrigo Duran on code complexity, for example. But this may be different for algorithms, and I haven't looked into that. However, when it comes to comprehension, you need to understand both and you need to connect both. And there is hopefully going to be a paper very soon on exactly that topic.
That's great. Okay, one comment from Gustavo that the presentation and video was really cool. So well done on that.
Thank you very much. Oh, I can give it
right.
too.
Okay, while we're waiting, we have, okay, I could ask one question. So, so since there are some differences between algorithm comprehension and program comprehension, what do you think? How can we help the programmer to understand the algorithm better when they write programs?
I think it would be more interesting to think if we write the whole algorithm, also including a proof, because if we are designing the algorithm for the classes, we should keep in mind that a student at a certain level of time, or maybe even an experienced programmer who has to study or is reading a paper, has certain concepts in mind how to solve things. Some of these may be like evolved plan schemata, so schemata how to solve certain processes. And if you write the proof accordingly, that you can, for example, support students or readers that don't have the plan schemata, or if you write the proof to help them connect the plan schema in the code with the proof, I think that would be very helpful to do that.
All right. Thanks a lot for the answer. Okay, I think we are at the end of this session, and I would like to let all the attendees know that there will be 10 minutes break before we start the next session, Impact on Code.